Okay, so if you've opened your test data, the first thing to do when you inherit a file is to have a look at your variables and see what you've got. So I always recommend go to your variable view first, because that gives you a breakdown of what variables you've got with a description. Okay, so you should recognise this as it's the study that you just took part in. So I've entered your data, and I had a data set already of around 60 to 70 students, so I've added your data to some previous data to give us a bigger sample. Okay, so you've got age, then you've got gender, and if you click on the values, you'll see that it's 1 is coded as male, 2 is female, and 3 is other. And then you've got your Coke-like, which is the score for liking Coca-Cola. And that was rated from 0 to 100, and then you've got your score for Asda-like, which was liking of the Asda Cola, again rated from 0 to 100. Okay, so we're going to go back to the slides from week 5. Okay, so we've done the taste preference study now. So you tried what I told you was Coca-Cola and Asda Cola when it was in fact both cups were Asda Cola. I primed you by telling you that it was Coca-Cola and showing you a picture of Coca-Cola on the screen. And then when you drank the second drink, I told you it was Asda Cola, and I primed you with having the picture of the Asda Cola on the screen. So we're going to briefly talk about this study, and then we'll move over to the data and have a look at analysing it. So we'll talk about what the experiment was, what our hypotheses were, and whether they were one-tailed or two-tailed, and how we'll test these hypotheses. So can you say what the hypothesis was? Anyone?
At students, yeah. If there's two drinks and they taste differently than each other.
Yeah, so that would be the two-tailed version of the hypothesis. The two-tailed version of the hypothesis would be that the drinks are rated differently, but that doesn't say which direction it was going to go. And we actually do have a direction. Yeah.
So the hypothesis is that the students would rate the drinks differently even though they're the same.
Yes. Yeah, but actually we can make that one-tailed. So we actually have a one-tailed hypothesis for this study.
So if we show a picture, generally they would have a preference towards Coca-Cola.
Yeah, exactly. So we predicted that the Coca-Cola would be rated higher than the Asda Cola because Coca-Cola is a big brand name, whereas Asda is here in the UK. If you're not from the UK, you might not even be familiar with Asda because they tend to be bigger supermarkets that are more out of town. But Asda is one of the budget supermarkets, maybe a level above Lidl and Aldi. So we predicted that the Coca-Cola will be rated higher than Asda Cola, just based on your expectations about Coca-Cola being a well-known brand around the world. So it is a one-tailed hypothesis because we're predicting that Coca-Cola will be rated higher than Asda Cola. And we're going to test it with a t-test, so which we'll move on to later in this class. Okay, the first thing we need to do is to check whether our data are actually ready for analysis. In this case, we don't need to like transform any variables or compute any total score, because we've got a score for Asda Cola and we've got a score for Coca-Cola, and we're just going to compare them. But we do need to check for outliers, and we do need to check for normality in our data set. So that's checking whether our variables are normally distributed. Okay, let's go to SPSS and we'll check for our outliers and we'll check for normal distribution. So open your data set, and the variables that we want to check for outliers are all of our scale variables. So let's check age first, and then I'll ask you to check Coca-Cola and Asda Cola. So if you go to Analyze, Descriptive Statistics, Explore, and move age into the dependent box. And then click Plots. Yeah. And click Histogram and untick Stem and Leaf, and click Normality Plots with Tests, and then you can click OK and continue. Analyze descriptive statistics. Explore. Analyze descriptive statistics. Explore. Move age to the dependent box. Just click the blue arrow. Just click the blue arrow. You click this blue arrow, it moves it without having to drag it. That's what it's click plots. Just histogram, unclick Stem and Leaf. Click here, normality. Okay, continue. Everyone okay? Okay, so you should get your output. So take have a scroll through your output and see like if anything looks interesting or unusual, like what's going on here. Yeah.
So we do age, we go to the dependent list.
Yeah.
And then we put plots.
Yes.
And then we put
Histogram. Yeah.
and we remove this down.
Yeah.
We always remove this down.
Yeah, I just don't find it useful.
Fair enough. And then the box plots the same as they are.
And click Normality Plots with Tests.
Thank you so much.
All right, so what's going on with age? What is going on with age?
We have two outliers.
We've got two outliers, yeah, so we can see them, if we scroll down to the histogram, we can see on the histogram we've got two outliers with age. So we now need to decide what to do with those outliers. You will pretty much always get this with a student sample, because the majority of students are in their early to mid-20s, and then but you'll have a string of older students in the sample. So this isn't unusual for the sample that we've got, but we need to decide what to do with them. So last week we discussed options that we can do with outliers. I don't agree with changing their ages to the maximum age that wouldn't be an outlier. That it is acceptable, but I don't agree with it. So my preferred options would be, the first option is we can keep them in, because it's just age. They've taken part in the Coca-Cola and the Asda Cola conditions, So each person is their own control. So in that sense, I wouldn't expect age to affect the results. The only result it might affect is when we come to look at to see whether there's a correlation between age and liking the drinks. With outliers, we would need to do a Spearman correlation instead of a Pearson correlation. That's okay. We can handle that. Or we remove them, and then we haven't got a problem with outliers in our data set. So I put it to you to have a vote. Okay, so your options are 1, keep them in, and 2, remove them from the data set. Okay, so hands up for option 1, keep them in. 1, 2, is that everyone voting? 1, 2, 3, are those hands up? 4, 5, okay, so 5 votes for keep them in, and was that a vote for keep them in? 6, okay. Hands up for remove them from the data set. 1, sorry, you're outvoted. Okay, we're going to keep our outliers in. It's just age, so I don't expect it will have a big difference, but when we come to do a correlation, we need to remember that because we've got outliers, we need to do the non-parametric correlation instead of the parametric one, which would be affected by the outliers. Okay. So we've checked age. I now want you to go ahead and check whether there are any outliers on the ASDA Cola and the Coca-Cola scores. So the same process that we just went through, but do it now for Coca-Cola and ASDA Cola, and see if we've got any outliers.
You do one at a time, right?
You can do them both together, actually. It will just give you your results. Will be together.
No, outliers.
Analyze descriptive statistics, explore.
Yeah, same thing as
Mm-hmm. Okay, has everyone managed to analyse Coca-Cola and ASDA Cola?
Mm-hmm.
Okay, so anything going on here? Anything interesting about these data?
No outliers.
No outliers, good. And so we don't need to decide what to do about outliers. If you scroll down to your histograms, you will see, your box plots, you'll see no outliers. What about if you look at the mean scores for Coca-Cola versus ASDA Cola? Anything interesting about the mean scores?
More like Asda.
Yeah, so ASDA Cola has a higher mean score than Coca-Cola. So this means that overall participants have rated the ASDA Cola as actually higher than the Coca-Cola, which is the opposite to our hypothesis. so what we're going to check is like, okay, that we can see just by looking at the numbers, we can see that the Asda Cola has been rated about 11 points higher than Coca-Cola. But what we want to do with a statistical test is see whether that difference is significant. So like whether it's really a meaningful difference. Okay, so we've checked for outliers. The other thing we need to check is normality, so whether our data are normally distributed. So scroll back up to the results that you got for age. And from looking at the histogram, like it looks quite skewed because we've got more people in their early 20s, a few people up to 30ish, and then we've got some outliers. It looks skewed to me, but we need to use Shapiro-Wilk to check whether it's significantly deviating from normal. And we already asked for that, so if you look just above your histogram, you've got the test of normality box. Okay, just above the histogram, this box for tests of normality. If you didn't click normality plots with tests, you won't have it.
Yeah, I don't have it.
Okay, so go back into analyze descriptive statistics and explore. In plots, make sure you tick this option, normality plots with tests. Make sure you click normality plots with tests, otherwise you won't have your normality test.
Did you click on
plots? Yeah, normality plots. It's okay. So you need to do put age in as well. Just put age in the same one.
Okay, thank
Okay.
you. So I have to
You okay?
No.
Right. You've got. Okay, I don't know. Yeah, you've done it for males and females, which you don't need. So click analyze, descriptive statistics, explore. Scroll down. This is one data set. Close this. Close. Close this. Open Blackboard. Can I use the mouse? Thank you. This one's for my daughter and this one's for my son. Where's Blackboard? You okay? You okay? Okay?
Yeah, I think so.
The graph for like Coca-Cola is positively skewed, but for Asda is a normal curve. There's no skew.
Looks like it, yeah. So
Almost
the test we need to check is the Shapiro-Wilk test. So for each of your tests now, you should have this test of normality box, and Shapiro-Wilk tells us whether it's a test of how much your actual data deviate from normality. And if it's significant, it means that your data do deviate from normality, which in this case is a bad thing. Like we want our curve to be as normally distributed as possible. But this test for looking at Shapiro-Wilk's test for age shows the p-value So look at the sig column, tells you your p-value. So that's the probability of the null hypothesis being correct. And in this case, it's less than 0.001. So there's a really tiny probability that the null hypothesis is correct, which means that in this case, our data do deviate from normality. So that's for age. So check now for your Shapiro-Wilk tests. You should have another test of normality for Coca-Cola and Asda Cola. And so I want you to have a look at those Shapiro-Wilk p-values and see whether our data are normally distributed for Coca-Cola and Asda Cola, according to Shapiro-Wilk. Coca-Cola test that you just took part in. So make sure you save those.
So if it's lower than 0.5, it means it's
0.05. It's 5%, yeah. Okay, so this is your data set now, so I'm just going to catch you up to where we've got to. So, age, this blue arrow, and raise them to that. Okay, now you're where we are.
So here the walk test is it's 0.2 and 4%, which
yeah. So
the null hypothesis. So anything below 5% is the null hypothesis, right?
No, if it's below 0.05, then I mean it's the probability that your null hypothesis is correct, but we accept it as significant if it's below 0.05, so which would be evidence that your hypothesis is likely to be correct.
Right. So if the sig value is 0.05, that means the hypothesis is correct.
Yeah, it's less than 0.05.
And 0.5 and higher is null hypothesis is correct.
Yeah.
So in this case,
0.05.
Yeah, 0.05.
Yeah, yeah.
So here, both are below 0.05. The Coca-Cola is smaller, that means there is a skewness.
It means there's more skew in the Coca-Cola.
Coca-Cola.
Which you can see in this.
Oh,
Yeah. All right, so your Shapiro-Wilk values, they're really small. So we've got, for Coca-Cola, we've got 0.002. So is that significant? Yes, it is, yes. It's smaller than 0.05. So that smaller than 0.05 is a significant p-value. Ours is 0.002, which means that there's only, if we multiply it by 100 to get a percentage, it means that there's only 0.2% chance that our data are normally distributed.
So that means our hypothesis
Means-
is not correct.
Yeah, so it means that they're not normally distributed, basically. What about this one? So liking of Asda Cola, we've got 0.004.
Same.
Same, yeah, it's significant because it's less than 0.05, which means there's only a tiny possibility that there's no, that our data are normally distributed. Okay, we can see that from looking at the histograms. If we look at there's our Coca-Cola histogram, which looks quite skewed towards the lower values. So generally people didn't like Coke that much. And then we've got, if we scroll down a bit further, we've got our histogram for liking of Asda Cola. This one to me doesn't look as skewed, but Shapiro-Wilk says that there is some problem with it. The problem with just using Shapiro-Wilk's test is it tells us that our data are not normally distributed, but it doesn't tell us whether the problem is with skew or kurtosis. So because we've got significant values for Shapiro-Wilk, we need to now have a look at skew and kurtosis to try and find out what the problem is, and you need to report this in your lab report. Okay, so we're going to scroll up again, and I'm going to we'll go through age together, and then I'll ask you to do the same for Asda and Coca-Cola. So if you scroll back up to the top of your output, to your descriptive statistics for age, and you'll see you've got values for skew and kurtosis. Okay, in your descriptives table, you've got a statistic and a standard error for skew and kurtosis.
Yes.
Okay. Now, just looking at those values, they're not very meaningful. Like it's quite difficult to interpret, like what these values actually mean, and whether, like, just looking at those values, like, can you really tell whether there is a significant problem with skew or kurtosis? So what we're going to do is what's called a Z test, which will give us a Z score. And now we know what Z scores mean. Anyone remember the cut-off value for a significant Z score?
1.9.
Yes, 1.96. So someone was listening.
Sure.
Okay, so we're going to do a Z test, which will give us a Z score, and then we just need to look at whether the Z score we get is above 1.96 or below minus 1.96, and then we'll know whether we've got a significant problem with skew or with kurtosis. The Z test you need to do manually, so get out your calculator. It's not difficult, but you do need to do it manually. Okay, so you've got a calculator app on your computer or your phone. And to do the Z test, we just need to divide the statistic by its standard error. So for skew, you just do 3.06 divided by 0.281. So the statistic divided by standard error.
So the statistic by the
Standard error, yeah. So those two columns in your descriptives table.
yeah. So which
So do skew first. Do skew first, and we'll check whether skew is significant. So 3.06 divided by 0.281.
that's above 1.92.
It's well above 1.96. I am surprised that it's that skewed. But yeah, so did everyone get the same as me?
Yeah.
Great. So you took from the descriptives table, looking at skew, the statistic of 3.06 divided by the standard error of 0.281. You should have got 10.89 if we round it to 2 decimal places. And that is a Z score. Okay, that division that we just did is the Z test, which gives us a Z score of 10.89, which is really big. It's much bigger than 1.96. So what we can conclude is that we've got a significant skew. We've got significant skew in our age variable. Okay, which we knew. So it's not a surprise. What we want to look at as well is whether we have a problem with kurtosis in our age variable. So you do exactly the same test. So look at your values now for kurtosis, and you do 13.64 divided by 0.555. So do that Z test, and we'll see what our Z score is for kurtosis.
24.6.
Is it?
24.57.
Okay, which is also really, really high. You need a calculator. Search. Count. Just use the mouse. I'm just going to get rid of some data that this is correct. I'm just going to use up the stuff that we have here, so it doesn't confuse. So we're looking at these values, so age you get skew here. So you do 3.06 divided by 0.281 to get your second test.
Yeah.
And so you need to use
What
your
about?
calculator.
Yeah, I know what it means. I guess it just means it's very skewed.
Divided by 0.281 in your calculator.
Just for the Z test, just to recap it quickly, we got a 10.88 and the cutoff is 1.96. So, like, do we usually get results around 1 point something or 2, like not that extreme?
Yeah, usually. I think it's because our age variable, like it is quite skewed. Well, like we already knew that. And age quite often will be, especially in student samples. So, okay, so we've done the Z test for kurtosis, which also came out really high. It's 24. And also, if we look at the histogram, we can see really that the shape of the distribution, I would say, is leptokurtic, because it's got a very high peak with the scores quite tightly clustered around the mean, apart from the outliers. So we can see that it is leptokurtic, and our Z score. Our Z score was around 24, 24.58. So that confirms that we do have a problem with kurtosis in our age variable. So when you write this up, you would just say something like that the variable, so age was checked for outliers and normality. You say that you found 2 outliers, but they were not expected to affect the results, so you didn't remove them. And then you'd say that Shapiro-Wilkes test showed that the data for age deviated from normality. And because Shapiro-Wilkes test was significant, you investigated further by doing Z tests. And the Z tests confirmed significant skew, and then in brackets you just put Z equals, I've removed it now, but Z equals 10.89. And then you and the Z test for kurtosis confirmed that there was a leptokurtic distribution or something like that. And then just in brackets, Z equals 24.58. Leptokurtic, the shape of the distribution is like it's leapt up. Leptokurtic for kurtosis. It's in the slides from, I think, week 3, where we looked at the shape of distributions. Okay, so something like when you write this up, try to be quite concise about the way you write it. So you just say that Shapiro-Wilkes test was significant, so Z tests were performed, and then just briefly report your Z test values and what they mean. Really, we need to show that you know that. You need to show that you know what these values mean. So you need to explain something like that there was significant skew, and then just report your Z score, and you need to say that there was excess kurtosis. And report your Z score. You can assume that your reader has got some level of understanding of stats, so you don't need to over-explain things. Like you don't need to explain that the Z score is significant because it's above 1.96. You just need to interpret it correctly, and that shows that you understand it. Does that make sense? Yes?
I have a question. I'm going to try explaining it because it's a bit confusing in my brain. But what I am confused as to this is like, okay, I understand like there's 2 people who are older, so they're the 2 outliers, and then we're doing this complicated thing to support that, which is like quite obvious from that, right? But then you said that the more the p-value when it comes to the Shapiro test is significant, the more likelihood of the hypothesis being incorrect.
Mm-hmm.
But we're looking at the age, and age is not mentioned in our
Right.
hypothesis.
In this case, the Shapiro-Wilkes test is only testing the hypothesis that the data are normal.
Okay,
So all the Shapiro-Wilkes test does is test whether your data are normally distributed.
like not our actual hypothesis.
Not your actual hypothesis.
Okay.
No, the Shapiro-Wilkes test only looks at whether the data are normally distributed.
Okay.
And
And what's the test that tests our actual hypothesis?
that we're going to move on to, and that's called a t-test.
Okay, got it. Thank you.
So, okay, so we've checked normality for age. I want you to now go ahead and check normality for Asda and Coca-Cola. So in the same way, so start by looking at Shapiro-Wilkes test, which we already looked at, and then so you need to go ahead and do those Z tests. Write down your Z scores because you'll need to report them in your report. Just a second. Okay, so it's this sig is your p-value, which is a probability. So Shapiro-Wilkes test tests whether your data are normally distributed. So like when you imagine that nice normal distribution shape on histogram, Shapiro-Wilkes test tests whether your data are close enough to that shape or not. And if Shapiro-Wilkes test is significant, it means that your data are significantly different from that nice normal shape. If it's less than 0.05, which this one is, it means your data is significantly different from that shape. That's all. You've done it. So this is your p-value, in the sig column. That means that your data is significantly different from normal. But it doesn't tell you whether the problem is with skew or kurtosis. So that's where you need to look at skew and kurtosis. You need a calculator.
And if you scroll down to the graph, if you see the histogram,
Okay, so you do
if you see the histogram is skewed to the positive side, this side, you see this is the higher one, this is the lower one.
so that divide that by
Or
that, and you
gradual,
get
yeah,
24.
it's so yeah, because it's
Also,
gradual rise
it's
in
above
gradual.
1.96, so it's
Whereas
which
you
means we
see
have a
this one,
significant problem with
it looks
ketosis.
more leptochronic to me
That makes
because
sense.
it's gradual.
So we did it together for
And
age,
then
write down the numbers
we
that you
can
got.
calculate the Z value from here. Then we did
Write down your Z
calculate
scores
the
of
co-component
10.
value.
So it's there in the margin of calculator, 10.89
Yes. To
plus
go to the
U,
go to the skewness, go to the
84.58
So
ketosis.
these are
and standard
and
is
then divide this by this, and then
0.143
divide this by this.
Yeah, yeah, so just write in a sentence.
So that is one component which is usually
And now do the same for Asda and Coca-Cola.
divided by half this one.
Who had their hand up? Sorry,
One thing divided by one.
I just wasn't here.
okay, so we were just looking at the Z scores. Z tests, weren't we? Where we did skew divided, we did statistic divided by standard error. Write down the values that you got from those. I've still got it open in the calculator on the board. Because those are your Z scores, so in your lab report you need to write something there. That Z tests showed that there was significant skew and ketosis.
Okay.
And you just need, and then it just in brackets, you just need to write their equals and then like that number.
Okay.
So do the same now for Asda and Coca-Cola and see if any of them are significant.
Okay.
Okay.
Yeah, so this is also minus 5, 1.5, which is which I think falls into the category 1.5.
Right. So what did you get for Asda and Coca-Cola?
So Coca-Cola is
10.
1.46 skewness.
So Coca-Cola 1.46 for skew.
Skewness.
So is that significant?
Not significant.
Not significant.
And
So
similarly for ketosis, it's minus 1.5. That is
Okay.
also not very significant.
also within the range of minus 1.96 to plus 196. Okay, so for Coca-Cola, although Shapiro-Wilkes test was significant, the Z tests were not significant. So probably it's some like combination of skew and ketosis together that's made Shapiro-Wilkes test significant. And what did you get for Asda Cola?
4.0.
Sorry,
For Asda, 0.4.
0.4, for, is that for skew?
Yeah, and then ketosis, is that negative 4.24?
Negative 4.24. So is that significant?
No, it's also in the range 1.96.
Didn't you say 4 point, negative 4.24?
Yeah.
Yeah, so it's below the lower cutoff of negative 1.96. So it is significant.
Oh, 0.125.
Sorry, say that again.
So the skewness for Asda is not significant.
Uh-huh.
So it's 0.40,
Correct.
and the ketosis is
Ketosis.
significant, so that's minus 2.149.
You've got different values.
Negative 4.2.
Let's just check ketosis for Asda Cola because you.
You're talking about ketosis or skewness?
We're talking about ketosis.
Ketosis is minus 2.1.
Okay, so for ketosis for Asda Cola, I get minus 2.15. Is it significant?
Yeah.
Yes, because it's outside of that range from minus 1.96 to plus 1.96. So because it's smaller than that negative value of negative 1.96, it is significant, which means that the Asda Cola data has an issue with the ketosis. Okay, so when you write this up, you don't need to report all the non-significant Z scores, but just say that you checked them. and the significant one was that Asda Cola had excess ketosis. Then in brackets, Z equals minus 2.15. So if you write this down now, you can use this as your section for your results section. Yeah. So you first of all say that you used Shapiro-Wilkes test to test normality, and that
You do that under the experiments.
Yeah, in your results section. You'd say that Shapiro-Wilkes test was significant, so you conducted Z tests, and the Z test for Asda Cola showed that it had excess ketosis. And then in brackets, Z equals minus 2.15. Okay, so you do that the same for each of them. So you need to open a Word document so that you can write this down. So you need to write a sentence. Age was significantly skewed. And then you just take the brackets for me. Age was AGE. That's it. Okay, so but you need to check. So the same calculation that you just did, you need to do for the skew and ketosis for age, and then also as the had excess ketosis, so you ketosis for Right. Everyone okay? Right. So thank you. Okay, so we've done the first stage, which is checking normality and outliers. We have found some outliers, and age was not normally distributed. So when we come to do the correlation, we'll just use the non-parametric correlation, which isn't affected by outliers or like skew or anything like that. We also, we don't have any outliers for our Coca-Cola and Asda Cola, but we do have skew on our Asda Cola. Was it ketosis? Yes, we've got excess ketosis on our Asda variable. What we're going to do though, we've got quite a large data set. It's 73 participants. And there's a theory called central limit theorem, which says that actually once you've got more than 30 participants in a data set, then if the data are skewed, then that's normal for that sample. So we have got more than 30 participants, so we're going to go ahead and use the parametric t-tests anyway, because we've got a big enough sample. And actually, if your data are a bit abnormal, these tests are quite robust to handle a bit of non-normality in the data. So we can go ahead and use the t-tests anyway, because we've got a big enough sample. We've got a sample of above 30. So when you write this into your lab report, you can just write a short sentence to say that because we have because our sample is above 30, according to central limit theorem, we can still use the parametric test.
According to
Central limit theorem,
Okay.
which essentially it says that once samples are above 30 participants, then any like skew or kurtosis is actually normal for that sample.
Okay.
So even though they deviate from that like nice normal distribution curve, central limit theorem says that even though they deviate from that curve, whatever shape curve they form is normal for that sample.
So these terms, like, for example, this one, the central limit theorem, and above we used leptocritic. Like these phrases, I know you use them a lot. So, but for someone who's never used these, how do we go about using them in our lab reports when we don't know what they are, or how to find them, or?
Leptokurtic we looked at in I think it's week 3 when we looked at the shape of distributions and we talked about skew and kurtosis. And central limit theorem is in the core textbook, the Andy Field one. He talks about central limit theorem and a bit more about like what it means. But that's basically it. It's a theory that says that above 30 participants, any deviation from normal is normal for them. So like the more participants you have, like the shape of their distribution is going to be normal for them. So if you've got skew in a, like let's say we collected the population of students and we looked at age, then their data being skewed is normal for students. So therefore it's okay to go ahead and use parametric tests because your sample is big enough to still get reliable results. Let's stop for a break, and then when we come back, we'll look at the t-test analysis.
Is a t-test correlation?
No. Correlation is looks at whether there's an association between two variables, like a linear association. T-test compares two groups, so we can compare the ASDA scores with the Coca-Cola scores.
Is there like a particular order where you would check everything? So like we're doing now, like first outliers.
Yeah. So this is it. We're doing it in all in order. So when you come to write your results section, just like you'll have this video to refer to, so you can just follow.
So next we're doing the t-test.
Next we're going to look at descriptive statistics. So we'll look at the mean age and the mean scores, which we've already done actually in the tests that we've already looked at. But we'll talk about descriptive statistics, and then we'll do the t-tests.
And then correlation.
Yes.
And then?
I think that's it.
Can you send me that? Like how, do you have it in the list?
Yeah.